Hi guys, Sajjad Hussain again with the new episode. In this new video, I am going to use the same model which I have used for last two models. This is an industrial building. I modeled and designed in last two episodes. Now I am going to further refine it and then I am going to design the connections, the base plate and the foundations. So let us start. To just cut short the time, what I did some modifications. Let me explain you what modifications I did it. In properties, of course, I did not do anything. All the properties are here, same as it is. But in loading conditions, what I did, because I have to design the foundation, so I added load cases for concrete design. These load cases are starting from load case number 28 to 40. And just to avoid these load cases in the design of this steel structure, I use the load list command and activated only load cases needed for the steel design. Besides that, I also added some parameters in concrete design. For example, this main one, so that the trusses will not be checked, these bracing members will not be checked against L over R condition. And then I defined the K values, defined the L values, and defined the yield. So these modifications I have already done just to suit the model and within the conditions. With all these modifications, let me run this model. Yes. Done. Oh, yes. Now let's go to connection design. In connection design, few connections we can design here. One of them is here. For example, this is the base plate. Let's see the load combinations. All the load combinations are there, and of course load combination generated for concrete design are not selected. That is okay. Now first I selected the base plate, one of them, and this base plate you can see how it is designed. Let me explain. First, this 0.04 and green means this is a very good design and safe. We can see it in a 3D. Here is the 3D. By default you can see that column is there, pedestal is there, base plate is there, and a huge foundation or pedestal. So we will modify it a little bit. But 0.74 means this is safe enough, and we can check the calculation also. So here is the result where we are going to check the calculation. In this calculation you can see all are green, so all conditions are checked over here. No warning, nothing. So let's fine tune. Sorry. Let us fine tune a little bit. Here on the left hand side we can see the information which is given. Load, all the lists are there. Steel design code is AISC 2010, allowable stress design, and the concrete will be designed as per ACI 318. Base plate dimensions are there. Minimum is 3 inch, minimum is 0.25 inch, maximum is 3 inch, increment is 0.125 of an inch. Now the base plate dimensions are maximum distance to edge is 15 and 1.5. This is the minimum distance, and in the other direction also the same thing. The embedded length is 12 inch, fine. The column here is tapered as it is mentioned, and these are the dimensions which are coming from the input model. Now the base plate selected is 17 inch by 17 inch and its thickness is 0.75. So this is 17 inch by 17 inch and its thickness is 0.75. Electrodes are E70XX. Column weld size is 5 by 16 of an inch. We don't have any issue. Now support here, the pedestal is 96 by 96 inch. We don't need that much. So let us reduce it to something around 24 inch by 24 inch. Still it is safe. It looks nice now. Embedment is, let it be 30 inch, a little bit longer. The concrete material is C4 and 60. That is what we were looking for. There are 2 anchor bolts on one side, 2 anchor bolts on the other sides, and let these dimensions be. The anchor bolt here selected is 1 by 4. Normally 1 by 4 is not a good anchor bolt size. Let us select half inch. No changes. And the embedded depth is 12 inch. Normally this is 12 times dia of the bar or dia of the bolt. So required is 6 inch minimum. We are providing 12 inch. That is okay. The material for the anchor bolt is ASTM F1554 and its grade is 36 KSI. So this looks a nice design. Let us save. So this is okay. Now what we can do, we can select one more point over here and let's try to design this connection. That means the column and this beam. These are the more important connections. So let us design this one. Here the beam number is 52 and the column is 57. So let us select this node and we are going to design this as a moment end plate, knee, beam column connection. This will be a vertical connection. So we will select this one. Okay. It will take little time because it will try a lot of options. So we have to wait for some time. It takes quite longer time. So we have to wait. What I will do, This is a typical connection which I will check, and I will design this connection. Rest of the connections are pretty simple. These are simple shear connections. It can be designed easily, no problem. And then I will design the foundation. So please bear with me. This is going to take a little bit longer time. You have to bear with me. It looks that I have selected a wrong point because it is taking a fairly good amount of time because it's doing a lot of iterations just to design a proper connection at this location. Oh my God. We have to wait. If you remember, we considered the seismic loading conditions. We considered the wind load also. So because of that, whenever a seismic load is considered, the knee connections like that has to be designed as per AISC Guide 4 or Guide 16. There are two guides which are used to design such type of connections, and of course STAD uses those conditions or those provisions. For the time being, I can show you those two. Let me see. Guide 16 is here. Yeah, this is flush and extended multiple row moment end plate connection. This is a very good guide, and I wish we can follow this guide. In case of an earthquake, we have to follow this one. I have already developed a MathCAD sheet based on this one. Maybe at some time I'll show how to use that one. But these are the conditions, especially for example, this type of connections are designed. This type of connections are designed as per this AISC Guide 16. All the procedures are given over here. So mainly these are various conditions where there are 4 bolt stiffened, there are 1 or 2 rows unstiffened, and the 1 by 3 rows, these are stiffened. All these conditions are given. These are all approved seismic connections. So here is the detailed procedure provided how to design these connections. Complete procedure is given. You have to follow all these procedures to design the moment connections, especially for this type of moment connections. Flow chart is also given. This is done, thanks God. But you notice this is red. Red means it's not good. So let us edit and see what the problems are. It should be less than 1. The ratio should be less than 1. So let's see what is the problem. The problems are highlighted over here. Transverse stiffeners, the thickness provided is 3, minimum is 4.37, so that is not good. Its thickness provided is 0.5, required is 1.25. Weld size is also not proper. Okay. Let's do first and see what happens. Here are the stiffeners. full depth stiffener are there. So this is the stiffener. Then the width of the stiffener is, maybe we can provide 6 inch. Let's see in a 3D view. Okay. Sorry. Undo. Anyway, pan is not working properly. Anyway, so you can see this is the stiffener plate, 6 inch. I can increase a little bit more. Maybe I can provide 7 inch. You can see now the plate is widened. Thickness is, instead of 0.5, let it be 1.5. And this fillet, instead of 3, it should be 9. So let's see the result. This is okay. Oh, again a new recommendation. No prying bolt moment strength. Okay, so the bolts are also need to be revised. Let's see the bolts, how many bolts we are providing. These are all fillets, bolts. The bolt selected is 3 by 4 of an inch and material is A325, not a good material. We should select 490 and 1 inch 490. That should be a good choice. Yes, that's a good choice. It is reduced to 1.04 and what else? Vertical bolt spacing, it should not be less than 2.67. We have provided 2. Let us revise. So vertical bolt specific spacing, number of rows of bolt, there are 2, and vertical spacing, normally it should be 3 inches. It's still 1.05, so we can modify. Oh, no prying bolt moment, 1.05. So maybe we have to select higher bolt. Instead of 1 inch, let's suppose 1.5 of an inch. Yes. Now this is 0.99. So what's still missing? It's still gray. Oh, outer bolt distance is 1.5. 1.5. It should be around 2. And okay. So it should be 2 inch. This should also be 2 inch. Here it suggests 28. very big value. Still something wrong. One missing. Only one thing is missing. That is inner bolt distance instead of 1.5. Let's say inner bolt distance. Internal bolt 2. Vertical spacing 3 inch. So let's see where it is now left. Inner bolt distance for with external flange. Inner bolt distance with external flange. Inner bolt. Here it is. Now it's green, 0.99. Let us save, close. It will take a little time. We can try to select one more. Let's select one more. This is a beam connected to a beam girder. Let's say shear end plate beam girder. It should be welded on one side, bolted on the other side. Okay, close. So there is no significant force, it's only 0.07. We can edit this one. It's okay, 0.07. We don't care that one. Let's save and close. So this is the way we are designing the connections. You can select as many connections as you want, and then you can select proper connection from the list of the available connections over there. And there are smart connections also. You can select. Base plate is selected from here, and there are some gusset plated also. You can select some gusset plates design also. It can be done. So it depends what type of connection you are going to design. You can select and design the connections over here. Just as a sample, I did the 3 connections, one the base plate, one as a knee connection, and the third one as a simple shear connection or a beam connected to a girder. Now I can go to foundation design. In foundation design, yes, I can include all the loads, and let's see. And we can start foundation. It's going to take some time to start anyway. So all the information from the STAD model is transferred over here, and let us fine tune this one. This is the main navigator. We can provide information about the project. We can write something over here. Asset type. Etc. Project number. Anyway. Revision history. Modeling view options. Skill setup. We are not going to do anything. Foundation plan, of course, it is there. We can set up a grid if we want to show the grids. It's not needed. Pedestal and anchor bolt, etc. The pedestal is there. Yes, we have to say that it has pedestals. So we have to click for pedestals. And if you remember, we selected the pedestal of 24 inch by 24 inch. That was minimum required. Here we will see what is the default value selected for the pedestals. Okay, so pedestals selected are 1.6814. Let it be for the time being as it is, because it will take some time to modify the size of the pedestal. Let us live with that pedestal. Now comes the loads. Here are the loads all. So what we have to do, load case number 1 to 6 are our primary loads, but load case number 7 to load case number 27, these are all service loads. So let us define them as service load. And after that, load case number 28 to load case number 40, these are all ultimate loads. So once we have defined that the service load and ultimate loads, that means the foundation will be sized based on service load, and the concrete or the foundation will be designed based on ultimate load. Let us create the job. Job title is isolated footings. Design code is US, fine. Default English, we can, yeah, or let's select SI. Code is ACI 31805. We can select 11, no problem. Okay, fine. Then we have to add all the available load cases so that load cases are considered, and we have to create a job. Now the job is created. Let's see the parameters. Concrete and reinforcement, let it be the default values. I'm not going to change. Soil and cover, of course, I want to change one thing. Let's assume that this is cohesionless soil, and let it be pedestal cover, not 50, it should be 75. It should be 75 as per the code. Unit weight of soil is okay. Now soil bearing capacity is 200. Rest we can keep as it is. Fine. Footing geometry, Okay, let it be the default value and let us design. Yes, let's save as. Let me put this as final. So file saving is started. We can see here the information provided. Now the iteration is started. It will take little time. Let's see. I want to share this design code, AISC design code with you. This is the extended end plate moment connection, seismic and wind applications. This is a special guideline, and this design guide is used to design the moment connections, and STAD is following this design guide. All these conditions are provided over here. I have also developed a MathCAD sheet which maybe later on I will show and I will share. So these are the conditions, or these are the approved connection, I can say, in seismic loading areas. So we have to follow these conditions. So whenever we are dealing with the structures in seismic zone, we have to be very careful for designing the connections. Only approved connections should be used, and approved connections are in the line of AISC guideline number 4. So this is the guideline. You can use this guideline to design the moment connections, either 4 bolts or 8 bolts. These are the conditions given. All these conditions are given, procedure is given, a very detailed guideline is this, and you should follow this detailed design guideline to design your connection. This design procedure, very detailed procedure is provided, step by step. All these calculations are there. At the end, examples are also there. So this is the summary of various cases, and at the end there are examples. Design examples are there. You can follow this design example to establish your own connection design. Luckily, STAT follows this guide, and the design of the connections are qualified for seismic loading conditions. So the design is complete. Here is the summary. The foundation geometry is 5.6 meter by 5.6 meters, and its thickness is 0.3 meter. Okay, we can live with that because we are not going to fine tune. And bars are also provided. A detailed report is available. All these are here. Only one thing, let us check. Okay, so these are the foundations design. Since the reverse loading conditions for wind etc. is not considered, that's why we can see the difference in sizes on left and right side. We can select the largest value. We can fine tune this one, no problem. The one thing which I wanted to check, that there should not be any overlapping, and of course these foundations are isolated foundations, they are not overlapping, so we can follow this design. This is the calculation sheet, detailed calculation sheet you can see over here. All these design calculation, loading condition, everything is there listed. So a very detailed design report is there. As if you are calculating manually, all the steps are there. How to check, everything is there. There is a warning that calculated spacing is more than required for the cracking conditions. Of course, then we can fine tune, we can reduce the spacing manually, and it can be controlled. So here is the complete procedure. Now you can see our structure over here. This was a simple industrial structure which was open from all sides. Only roof was there, and the columns were tapered. The part of the beams were tapered. The column to column distance was 37 meters, and we completed the whole design in 3 videos. The first video was the modeling, the second video was the design of the steel structure. Now this third video is about the design of the moment connections, or design of the connections and the base plate and the foundation. So now these 3 videos give a complete understanding of the design process of a steel structure. I hope it will be a good information for you. Please do not forget to subscribe and like my channel. Thank you very much. Bye.